Hello APC Mechanics students in Unit 1 Kinematics, Class 11, Calculus Approach, Part 5. So Section 1 Trigonometric Integrals. Previously we have introduced specific type of integrals related to polynomial functions. Now we're gonna continue this path and introduce integrals related to another functions and methods of integration. Some integrals of trigonometric functions are given by integral of cosine at plus b dt is 1 over a sine at plus b, and the integral of sine at plus b would be minus 1 over a cosine at plus b, where a and b are constant and c would be the constant of integration. Now recall that in the case of a derivative, the derivative of a sine is a cosine and the derivative of the cosine is minus cosine. Then here, because it's the reverse process and you can try it, we need to do it the other way around. Then the integral of cosine would be a sine, the integral of sine would be a negative cosine. And if you remember that, in the case of the derivative, we used to multiply by the derivative of the inner function. Here we're dividing by the derivative of the inner function. This is a linear, its derivative is gonna be a constant, and here also we're dividing by the derivative of the linear function, which is a constant. Okay. Other trigonometric integrals requires specific methods of integration. Remember that in the case of the derivative, we didn't put any condition that this rule is limited to certain types of function. But in the case of the integrals, things gonna be more complicated. We are only limited to the functional integral, in which the inner function is only a linear function. Alright, so till this moment we don't know how to integrate functional trigonometric functions in which that the inner function is not a linear function, for example a quadratic. Also we can say if a is 1 and b is 0, then the integral of cosine t dt would be sine t plus a constant, and the integral of sine t dt is negative cosine t plus a constant. This also holds, and here I'm introducing the general form of these integrals. Now example 1, compute the following integrals a and b. Let's start by part a. So this is straightforward. The integral of cosine 4t, then this is gonna be a sine, and the derivative of the inner function is 4. We're gonna divide by 4, and the result would be 1 over 4 sine 4t plus the constant. Similarly, for integrating sine negative 5t, then the inner derivative would be negative 5, then we're gonna divide by negative 5, and the integral of sine, so this is a mistake, this should be written as integral of sine minus 5t dt, and the integral of sine would give us minus cosine. So that would be the first negative is because we're going from sine to cosine, and the other negative is due to the derivative of the inner function. Negative and negative would cancel, and the result would be 1 over 5 cosine negative 5t plus constant. Now what about exponential integrals? Given the following exponential function, f of t is e to the power at, where a is a constant, then its integral with respect to time is given by the integral of the function f, which is the integral of this one. Now remember, in the derivative we used to multiply by the coefficient or the inner derivative. Here we're deriving by the inner derivative. Okay, and c is the constant of integration. Other exponential integrals require specific methods of integration. Similarly here, in contrast to the derivative, in the derivative we didn't put any conditions related to the inner function u, whether it's linear, quadratic, etc. Here in this case, whenever we're integrating, the condition is that the inner function is only a linear function. Now whether it's at or at plus b, we're gonna see it's perfectly the same, but here I'm considering the case where it's at. So in this case that would be EAT divided by a. Example 2, compute the following integral of a minus 3t dt. Then we're gonna apply the rule. Simply we divide by the inner derivative, which is negative 3. And another representation would be negative 1 over 3 multiplied by the exponential function. Now example 3, compute the following integrals a, b, c, and d. And you can notice that in part A, it's given in the form of at plus b, the inner function, and we're gonna see how to handle this via the previous rule. So let's start by example 3, part A. Then it's integral. Now we can drag 3 out because it's a constant. Now we can utilize the following, that e to the power minus 9t plus 1 can be written as e to the power minus 9t multiplied by e to the power of 1, and I've used the formula e to the power a plus b is given by ea multiplied by eb. Now e to the power of 1 is a number and it's a constant, it can be dragged out. Then outside the integral we have 3e, integral e minus 9t dt, and here we can integrate this safely by dividing by the coefficient, which is negative 9, which is the inner derivative, and no need to simplify, we can keep it like that, knowing that 3 can be divided by 9. Now for part B, we have a composite function 9 minus 5t plus an exponential function. Now we can divide the integral into 3 integrals. We can drag 9, 5 and 18 out. The constant here we have a 1, that would be a linear term, which is t. The linear would be t squared over 2, and the exponential we divide by the inner derivative, and that would be 100. And here for sure we can simplify by 18 and 100, so we can divide 18 by 100. Now for part C, we have the integral of 5 cosine 2t dt. We can drag the 5 out, it's a constant. Now what about cosine 2t dt? Cosine would give us a sign without a minus sign, and we're gonna divide by the coefficient, which is the derivative of the inner function, and that would be 5 over 2 sine 2t plus c. Now what about this linear combination of trigonometric functions? We can split it and drag the coefficients out. That would be minus 5 integral of sine 8t dt minus 3 integral of cosine 4t dt. Now sine would give us minus cosine, which cancels with this minus, and we divide by the inner derivative, that would be 8. And here we do perfectly the same, we divide by the inner derivative, which is 4, and the final answer would be that. Now section 3, logarithmic function expressed as an integral. The logarithmic function can be defined as an integral. Then ln t is the integral of 1 over t dt plus c, where c is the constant of integration. Now what I'm trying to say in this section is that the logarithmic function itself can be defined by the integral of 1 over t dt. Now let me explain the following. Suppose we have the integral of 1 over t squared dt. How can we solve this integral? We can utilize that t squared can be written in the form of a polynomial of a negative power, which is integral of t minus 2 dt. Then we increase the power by 1, that would be t minus 2 plus 1 over minus 2 plus 1 plus c. That would be t to the power minus 1 over negative 1 plus c, which is basically minus 1 over t plus c. But remember that here I'm using the rule which is given by a t to the power of n dt. Remember that we have put a condition on t on n such that n is different than negative 1. What does n equals to negative 1 stands for? If t is to the power negative 1, that would be 1 over t. For this reason, we have excluded the value for n is equal to minus 1, because 1 over t, the integral of 1 over t, is usually known as the ln function. So remember that the integral of at to the power of n dt holds for every value of n except for negative 1, because when n is equal to negative 1, that would give us the definition of the logarithmic function. Example 4, compute the following integrals. Let's start with part A. Integral of 1 over t dt, that would give us perfectly the ln function plus a constant. Now here you can ask yourself, okay, on the right hand side, c is given by, or the constant is given by plus c. If we drag it to the other side, that would be a negative c. So here we should put it as negative c. But the thing is that we're making use of the fact that the constant of integration is not fixed unless we know the initial or final conditions of the system. So negative c can be transformed into c, because later on we will fix the value of c. So basically I'm using the set of rules that say anything multiplied, any number multiplied by a constant would remain a constant. Constant added with a constant would remain a constant. Constant divided or multiplied by a constant would remain a constant. Why? This set of constant can be considered itself as the constant of integration, which will be later calculated using the initial or final conditions. Now, integral of 3 over t dt, we can drag the 3 out. That would be 3 integral of 1 over t dt. So here, for example, we have dragged the 3 out, and that would be 3 ln t plus the constant. What about integral of 1 over t squared? Here we can utilize that this is a polynomial. It can be written in the form of a polynomial with a negative power, which means integral of t to the power minus 2 dt. Now we increase the power by 1 and we divide by the final power, and that would be minus 1 over t plus the constant, or we can keep it like this. Now, section 4, methods of integration, change of variable. Integrals expressed as mixed product between different functions like t e to the power of t, t cosine t, ln t, t over t squared plus 1 require specific methods of integration like change of variable and integration by parts. So far, the operations that have been introduced on the integrals are basically addition, subtraction, and the integrals of polynomial, trigonometric functions, and exponential functions, and the integral of 1 over t, and we were limited to specific type of functional integrals. Now, what about integrating functions expressed as the product of two functions, or the division of two functions? Here in this case, we are multiplying a linear term by an exponential. We're multiplying a linear term by a trigonometric. We're integrating logarithmic function. We're integrating the ratio of two functions, which is a rational function. However, in this section, we will introduce the change of variable method. We will integrate, or we're interested in integrating t over t squared plus 1 using the change of variable technique or method. So how we're gonna proceed with this method? First of all, we need to understand when to use this method. If you look carefully at this integral, it consists of two functions, t and t squared plus 1. And if you can notice that the denominator, which is t squared plus 1, is a quadratic, and if we derive the quadratic, it would give us a linear, which is related to the numerator. So then basically we use the change of variable technique whenever the integral itself consists of two functions that are multiplied or divided by each other such that the derivative of one of the functions is related to the other. The first thing to do is to consider a change of variable, or we define a new variable u that is related to one of these two functions, and here our choice should be wise. In a sense, we have two functions given by t and t squared plus 1. We can say that u is equal to t or u is equal to t squared plus 1. We have two choices. Then which one we're gonna consider? We're gonna consider this one because t squared plus 1 compared to t is the stronger function, in a sense that, or has the higher power, in a sense that. Now if we try to derive this is a quadratic, it would give us a linear which is related to the numerator. Then I repeat, the first step is to introduce a new variable which is u, related to the one of the two functions that we have here, and our choice would be the stronger function. Now the second step, I named this step to be the differential step, is to use the identity which is u prime is du by dt, and try to express dt in terms of du by doing the following. If the derivative is given by du by dt, this is nothing new because we're saying that the derivative is du by dt, so the comma notation is related to the fraction notation. And in this case, if we try to isolate du would be given by u prime multiplied by dt. So here I'm saying that we're gonna express dt in terms of du by using this relation. Then we have, if we're saying that du is u prime dt, then keeping du as it is, keeping dt as it is, but we know that u is t squared plus 1, u prime is the derivative, the derivative of this is 2t, then u prime can be replaced by 2t, which is the derivative of that. Then we have a new relation between t and dt. The idea behind this step is to convert the integral completely, instead of being parameterized by t, to be parameterized by u. The first thing that we have done is change this into u. So we are done with this. But what is left is to convert t and dt into du, and this is done by the differential step, because now if you notice carefully, we have achieved this relation. We can isolate t dt, then t dt would be given by du over 2. Then t td would be given by du over 2, and by that, the integral given parameterized by t now can be completely parameterized by u. Now here, I have dragged t out of the fraction, that would be 1 over t squared plus 1 t dt. We know that this is u, and that would be du over 2. Then this can be expressed as, now here we have a coefficient which is half, can be taken out, and we're left with half integral of 1 over u du. And we know that now we can integrate safely, because everything is parameterized by u, and the integral of 1 over u is given by ln u, and here we don't forget the constant. And because we've started with an integral parameterized by t, our final answer should be parameterized by t, but we know that u is given by t squared plus 1, and that would be half ln t squared plus 1 plus c. So let me write here the different steps that we use in the change of variable method or technique. So step 1 is to do the change of variable, so defining what is meant by u. Step 2 would be the differential step, which is basically this one here. Step 3 is to convert the integral completely from dt to a integral given by du. And step 4, to integrate, then express our answer, the final answer, as function of t. This method works when one of the functions inside the integral can be expressed as the derivative in terms of the other, and for sure here the challenge is that, or the challenge always appears whenever the functions are multiplied or divided. If they are added, that would be straightforward, because we know how to integrate each function separately. Now let's compute the following integrals. As you can see that these are not intuitive, in a sense that they are complicated. Okay, we agree. But for part A, we notice that this is quadratic, this is linear, so the derivative of this would give us that. Then we're gonna use the change of variable. What about the tangent t? Tangent t can be done as sine t over cosine t, and we know that in this case, sine and cosine would be related via derivatives. And what about part C? In part C, we have, you can consider it as two functions, numerator and the denominator. The numerator is a constant function, which is 1, and the numerator, yes, is a constant function, which is 1. The denominator is a linear function, but the derivative of the linear would be a constant, which is related to the numerator. Then let's start. Then the first step is to choose the variable. Here we have two choices. Either we assigned it to this or to that. This is the stronger one. We're gonna say that u is t squared plus 2t. The second step is to be the differential step. Then du would be the derivative of this, which is 2t plus 2 multiplied by the differential dt. And here I'm using the identity u prime is du divided by dt. Then we need to convert this integral completely from t to u. Already this have been assigned to u. Now what about 1 plus t dt? We need to make use of the differential step. Here we can factor 2 out. That would be du is 2 into t plus 1 dt. If we isolate this, which means that 1 plus t dt is given by du divided by 2. So this and this would be replaced by du divided by 2. Okay, then our integral would change into integral du over 2 multiplied by u. we can factor out half, and the integral, so here we've ended up with an integral completely parameterized by u, which is linear. That would give us u square over 4, u square over 2 multiplied by half, that would be 4, and finally we would replace the final answer as function of t. Now what about the integral of tangent t dt? So you can utilize that tangent t is sine t over cosine t. Now the first step is to assign a new variable or function with one of these. Here the change of variable works because we know that both they are related to each other via a derivative, but the thing is that to which one we're gonna assign u, the numerator or the denominator. You can check out both methods and it's gonna be easier for us to assign the denominator to be the function u. So I'm gonna say that u is cosine t. This is the first step. Then the second step is the differential one. Then we have that du would be the derivative of cosine t, that would be minus sine t, and we don't forget the dt. And now we need to convert completely this integral to be parameterized by u. Already we know that this is u, so we can replace it by u, and from this relation we can say that sine t dt would be assigned by negative du, so this would be replaced by negative du, and the integral would becomes negative the integral of 1 over u du, and that would be minus ln u because we know that the integral of 1 over u would be ln u. And finally the final answer should be parameterized by t, and we know that in this case u is given by cosine t, so we replace u by cosine t. Now what about integral of 1 over 3t plus 5? The stronger function is gonna be 3t plus 5, so we're gonna consider that as a change of variable. Now for the differential step, du would be 3 dt, but in this case the numerator is given just simply 1 multiplied by dt, which is dt, so we need to find dt. Then in this case dt is given by du over 3, and now we're ready to convert this integral completely from t into u, and that would be 1 over u multiplied by du over 3. We can factor out 1 over 3, and that would be 1 over 3 ln u, and u can be replaced again back by 3t plus 5. And now by that, in section 5 we can complete the table of integration. The constant, its integral or antiderivative, would be a linear term. The polynomial, we increase the power and we divide by the final power. A would not affect anything, but remember that this only holds whenever n is different than -1, because for -1 we're dealing with the definition of the logarithmic function. For the trigonometric cosine of a linear function, that would be 1 over a sine the linear function. Sine of the linear function, that would be -1 over a cosine of the linear function. Remember that going from sine to cosine, in this case we have a negative sign, unlike or opposite to the derivative. The integral of a functional exponential in which the inner function is a linear, that would be the exponential function itself divided by the coefficient, and the reciprocal function 1 over t is assigned to be the definition of the logarithmic function. And now exercise 1, an equation for the motion of an object is given as 2vt minus 4x is equal to bt squared, where b is a constant. The variable v indicates velocity in meters per second, so v is in meters per second velocity, t is time in seconds, and x indicates displacement in meters. We're asked about the unit for measure of b. We can do it in two ways. Let me explain for you the first method. So what we're trying to do here, we don't know much about b, we know what is v, t, and x, and we need to find the unit of b. Now this, let me start by the first one. So this is the equal. Now for the left member we have 2vt. 2 has no unit, we suppose. V has a unit of meter per second, so time has a unit of seconds, so don't worry about the negative, and 4 we can ignore the 4. X is a position which has the unit meter. Now b, we're gonna keep b, and t to the power of 2, that would be seconds square. So that would be second and second would cancel. That would be meters minus meters is equal to b second square. Meters negative meters, so whenever quantities in physics are added and subtracted, they have the same unit. The final answer would be the same unit. That would be meters is equal to b second square. Then in this case, b is equal to meter per second square. This is one way to do it. Another way is that to isolate, since we're interested in determining the unit of b, we're gonna isolate b, and that would be, so this is the first one, b would be given by 2vt minus 4x divided by t square. Now 2 has no unit, v has unit of meter per second, t has unit of seconds, 4 has no unit, x has unit of meter divided by the unit of t, which is second to the power of 2. That would be, this would cancel, meters minus meter over second square. That would be meters per second square, and the correct answer in this case is C. Now exercise 2, a block of mass m is pulled from rest along a horizontal surface by horizontal forces. Magnitude is given by the equation F is AT plus B, where A and B are constants with appropriate units. The coefficient of friction between the block and the surface is mu k, which expression correctly relates the velocity of the block as a function of time. I know till this moment we didn't talk about the dynamics. How is the kinematics related to the forces? But I suppose that you have the following relation as a given. A is given by F minus mu k mg divided by m. So I suppose that this relation is given in this exercise. We will study in Unit 2 how to determine this relation from scratch. We're interested in the velocity. We know that the velocity is related to the acceleration via calculus and specifically integral. So v is the integral of a dt. And they're telling us that the block starts from rest, so the initial speed would be 0. Now we're not gonna worry about the constants of integration. Now that would be the integral of f minus mu k mg divided by m dt. Now we can replace capital F by the linear function. That would be integral of at plus b minus mu k mg divided by m dt. Now we can split the fraction into the following. So integral of at over m dt plus integral of b over m dt minus integral of mu k, m and m cancels, g dt. Now a over m is constant, t is linear, that would give us a quadratic, at square over 2m plus b over m, this is a constant, here we're left with one, that would be t. These are constants, minus mu k g, and for the final step, that would be t, we can add the constant of integration plus c. Because all of these are polynomial functions and this is v, then the constant of integration would be the initial speed, and we're starting from rest, that would be 0. And in this case, if we compare perfectly, the correct answer would be C. Then that's it for me in this video, guys. See you soon in a new one.